Hi class, in this recording we're going to talk about acid-base disorders and how we compensate them. So as we dive into it, thankfully there's not going to be as many chemical reactions as we had in the last recording. This one's going to be a little bit more gentle. As we look at acidosis, acidosis is when we have a pH below 7.35 in our extracellular fluid. And in these situations, because we have acidosis, too much acid, we have excessive amounts of hydrogen ions. And if we have excessive amounts of hydrogen ions, the concentration outside of the cell of hydrogen ions is elevated, and hydrogens tend to move into the cell via diffusion. As hydrogens move into the cell via diffusion, those positive hydrogen ions displace potassium ions, and the potassium ions are pushed out of the cell, while the hydrogen ions bind to proteins, negatively charged proteins within the cell. So the addition of those hydrogen ions is going to be buffered by a lot of intracellular proteins, so we don't have a overall loss of cations within the cell, but we do have help hyperkalemia result in that we have too much potassium outside of the cell. And as we have potassium moving outside of the cell, think back to when we talked about action potentials with the nervous system. During that repolarization phase, we move potassium ions out to lower the overall membrane voltage on the inside. And if hydrogen ions are displacing potassium ions and kicking them out of the cell, that's going to lower the voltage below baseline and causes the membrane to become hyperpolarized. So if we have these hyperpolarized cell membranes, that means in order to initiate an action potential, we have to raise the voltage up that much higher to get to the threshold voltage that triggers the action potential. So during these hyperpolarized states, it's very difficult to stimulate muscle cells or nerve cells, neurons, and we have an overall depression of the central nervous system and a reduction of electrical activity within the electrically active cells of our bodies. This reduction in the electrical activity leads to confusion, disorientation, and ultimately may lead to death if it goes untreated. If we have alkalosis, alkalosis is when we have an extracellular pH of above 7.45. And in this situation, we do not have enough hydrogen ions in the extracellular fluid. That's going to cause an overall net movement of hydrogen ions out of the cell. As those hydrogen ions are moving out of the cell, they are going to be displaced by potassium ions. So we have potassium ions that rush into the cell to displace the hydrogen ions that have been rushing out. And now we have excessive amounts of hydrogen outside of the cell to help reestablish pH. But the concentration of potassium in the cell has been elevated, and the concentration of potassium outside of the cell has been lowered. We have hypokalemia as opposed to hyperkalemia. So in this situation, our membrane slightly depolarizes as we have more potassium diffusing in. And that's going to raise the membrane resting state closer to threshold. And if that resting state is closer to threshold, a smaller stimulus can initiate an action potential. This results in muscles and neurons within our nervous system that are overactive. We have too much electrical activity. This can cause our bodies to have spasms, tetany, convulsions, or respiratory paralysis, all associated with too much electrical activity of these electrically active cells. We find that a person can't live for more than a few hours if their blood pH is either below or above these critical thresholds, 7.0 versus 7.7. And if we alterate the blood pH even further to a 6.8 to a 7 or an 8.0, that kills the person in a very short period of time, minutes. So these fluctuations in pH, whether we have acidosis or alkalosis, have very profound effects on the body by altering the electrical activity of the muscular cells, and neurons within our body. So if somebody has respiratory acidosis versus respiratory alkalosis, respiratory means it's associated with, well, the respiratory system. Acidosis means we have too much acid in the blood. So if we have the rate of alveolar ventilation lowering, it fails to keep pace with the amount of carbon dioxide being produced, that we will have carbon dioxide building up in the extracellular fluid, causing the body's overall pH to go down. This is very common if there's any kind of disorder that reduces our ability to breathe in and breathe out. Any kind of COPD, restricted or obstructive disorder. And a common example of that is emphysema, where we have very few functional alveoli in our lungs. We can have respiratory alkalosis when we breathe in and out too much. So if we're eliminating carbon dioxide faster than our body's making the carbon dioxide, that is going to lower the carbon dioxide concentration in the extracellular fluid, notably the blood plasma, and elevate the body's pH, resulting in alkalosis. So as we look at these two conditions, respiratory alkalosis, the one that I run into all the time, is lightheadedness. When I blow up lots of balloons, or maybe I have some hot food on my dinner plate and I'm blowing really hard on it, a lot of times I get dizzy and then I'm like, whoa, I need to stop. So that's me mechanically overventilating on purpose. Other people hyperventilate because they have respiratory alkalosis because of a psychological condition, maybe some kind of anxiety or fear causing them to hyperventilate. And when that happens, they can have all these side effects associated with respiratory alkalosis. When we have respiratory acidosis, we have the opposite. So instead of breathing in and out too much, we don't breathe in and out enough. Most people run into respiratory acidosis because they have some kind of disorder of their lungs or because they're holding their breath too long on purpose. We also can have metabolic acidosis and alkalosis. So when we looked at respiratory issues, it was because we were breathing in and out too much or breathing in and out too little. From a metabolic perspective, metabolic acidosis is when we make too many acids, in particular organic acids. So lactic acid, phosphoric acid being the two big ones. Or we could have fatty acids being produced. So if we have too many organic acids being pumped out in our bodies, we can have metabolic acidosis. Metabolic acidosis is commonly associated with alcoholism because there's a buildup of ketone bodies as a byproduct of processing alcoholism. And metabolic acidosis is commonly associated with diabetes, mellitus, as we have a breakdown of the triglycerides associated with that diabetes. Metabolic acidosis can also be due to ingesting too many acids. In this case, acidic drugs can induce metabolic acidosis, or if somebody has the loss of bases from their body, maybe they're having chronic diarrhea or they have overused laxatives, they're defecating too much, they are going to lose too many bicarbonate ions, sulfide ions, and phosphate ions, negatively charged ions from their body, resulting in their body having an overall acidic fluctuation. We also can have metabolic alkalosis, and this is really, really rare because we don't have a lot of situations where we eat too many basic food products. But maybe, just maybe, there's something going on where somebody is ingesting too many bicarbonates. Usually this would be somebody who has heartburn, and they're ingesting too many antacids, too many Tums. Or somebody was given an inappropriate amount of a bicarbonate solution intravenously. That could induce metabolic alkalosis. Or if somebody has chronic vomiting, if you vomit too much, you lose the hydrochloric acid from your stomach, resulting in an overall net reduction of the amount of acid in your body, shifting your overall body's pH to become more alkaline or more basic. So as we look at metabolic acidosis, here's a figure showing you some common symptoms of metabolic acidosis. And then here's another figure showing common symptoms of metabolic alkalosis. So whether it's acidosis versus alkalosis, it's the metabolic part that I want to focus on here. It's going to be either producing too much acid or removing too much base from our body or gaining too much base from our body. We very rarely will remove too much acid unless we have that chronic vomiting. In terms of the symptoms, the overall symptoms can be, for the most part, the same between respiratory and metabolic, alkalosis and acidosis. So how do we compensate for acid-base imbalances? Well, as a general rule of thumb, if we have a metabolic cause, we have a respiratory solution, and vice versa. If we have a respiratory cause, we have a metabolic solution. So the kidneys will compensate for respiratory problems. The respiratory system, the lungs, compensate for metabolic problems. And as we look at this arrow this column right here, the pH, I want you to think of this as what's happening when we have our condition. So if we have metabolic acidosis, our blood pH is too low. If we have respiratory alkalosis, our pH is too high. If we have respiratory acidosis, our pH is too low. And metabolic alkalosis, the pH is too high. So here's the problem, and I would prefer that this figure be over there, but we'll work with it. So when we have metabolic acidosis, our pH is too low. The primary cause of our pH being too low is that we have a decrease in the amount of bicarbonate ions in our bodies. And to compensate for that decrease in bicarbonate ions, our bodies will lower the partial pressure of carbon dioxide in the bloodstream. In other words, we increase the rate of ventilation, and if we increase the rate of ventilation, we are going to ultimately raise the body's pH to compensate for the initial lowering of our pH. If we have respiratory alkalosis, our blood pH is too high, it's alkaline. The primary cause of respiratory alkalosis is that we don't have enough carbon dioxide in the blood. We have decreased blood carbon dioxide. In response to that, our kidneys are going to excrete out more bicarbonate ions into the urine. We'll make our urine more alkaline. So the amount of bicarbonate ions in the blood goes down, and by lowering the amount of bicarbonate ions in the blood, the overall pH of the blood will be lowered in response to the initial raising of the blood pH because of respiratory alkalosis. If we have respiratory acidosis, we find that we have too much carbon dioxide in the blood. We've been holding our breath too long, or we don't breathe in and out enough. So the primary cause of respiratory acidosis is that the blood carbon dioxide concentrations are too high. In response to elevated blood carbon dioxide or acidic respiratory acidosis, our urinary system will respond by increasing the amount of bicarbonate ions in the bloodstream. And as we add more bicarbonate ions to the bloodstream, that will cause the pH of the bloodstream to go up because bicarbonates are alkaline. And we will raise the blood pH in response to the initial lowering of the blood pH. As we look at metabolic alkalosis, this is when we have an alkaline pH or our blood pH is too basic. And this is typically going to be initially caused because we're making too many bicarbonate ions and dumping them into the bloodstream. And to respond to too many bicarbonate ions in the bloodstream, our body compensates for that by increasing the partial pressure of carbon dioxide, so we don't breathe in and out as much. And as we have more carbon dioxide being dumped in the bloodstream, we will have more carbonic acid, and that carbonic acid will lower the blood pH in response to the initial elevating of the blood pH when we had the alkalosis. So that's how the various systems can compensate for each other. If we don't compensate for it, if it's uncompensated, we typically are going to have some kind of clinical intervention if our body can't do it by itself. And if our body can't do it, that's going to be categorized as uncompensated. So as we look at these respiratory compensation mechanisms, these respiratory mechanisms can work over the course of minutes by altering the amount of carbon dioxide that we inhale or exhale to ultimately change the pH of our body fluids. If we have hypercapnia, too much carbon dioxide in our bodies, we are going to stimulate the pulmonary ventilation or respiratory rhythm so that we breathe in and out more, lowering the overall carbon dioxide concentration of our bodies and allowing the pH to become more alkaline. If we have hypocapnia, not enough carbon dioxide in the body, we're going to lower the respiratory rhythm so that we allow more carbon dioxide to build up in the blood, making more carbonic acid and ultimately lowering our blood, acidifying the pH in response. As we look at renal compensation mechanisms, these can tend to be a little bit more complicated. We can adjust the pH of our body with our kidneys by changing how much hydrogen ions we secrete into the urine. This is a slower mechanism that works over the course of days, but ultimately it's better because we will eliminate the hydrogen ion from the body, not just bind it to a chemical storage molecule or buffer. If we have acidosis, we have too many hydrogen ions in the body, and the urine will have its pH drop because we dump more hydrogen ions into the solution. And the renal tubules will increase the amount of hydrogen ions they dump into the urine and the amount of ammonia that we have in order to buffer it so that we can ultimately elevate the pH in the body. So in response to that acidosis, we urinate out more acid and raise the pH of our body. In response to alkalosis, we are going to urinate out H3CO, and this is a typo here, this should be CO3 with a -1 charge. So we're going to urinate out these bicarbonate ions in an alkalosis situation. So we have elevated elevated urine pH. So the renal tubules are going to decrease the rate of hydrogen ion secretion, allowing for more bicarbonate to be excreted and lowering the overall pH of our body in those situations. Our kidneys, though, don't act very quickly. It's more of a long-term solution. We can't compensate for pH imbalances with our kidneys. Our short-term fixes are typically going to involve our respiratory system or our chemical buffering systems. However, the kidneys are very effective at compensating for long-term pH imbalances that last for days or weeks. So that's all we have for this recording. If you have any questions or comments, please feel free to post them in the class discussion boards or to shoot me an email. And as always, happy studies.